Hi guys, here is MIH. Ion exchange membranes are very useful devices in electrochemistry for conducting some very useful and seemingly impossible reactions, like splitting a salt to its constitutive acid and base simultaneously. However, these membranes are notorious for being out of reach for amateur chemists, either because most online stores don't sell it, or because of its prohibitive cost. In this video, I'd like to approach this problem by providing a guide on making ion exchange membranes in an amateur lab setting. This video is of pure theory and features no experiments, but rather draws information from research papers and 3 YouTubers who have generously shared their methods for DIY ion exchange membranes. By the way, the first part of the video is about the structure and synthesis of commercial membranes, so for those of you who just want a working procedure for DIY membranes, please skip forward along the video. Let's begin by briefly explaining why we bother to make ion exchange membranes. As its name suggests, an ion exchange membrane is a polymer-based membrane that is only permeable to cations or anions, and not the other. In other words, it only allows positive or negatively charged particles to pass through it. Its principal application is in aqueous electrolytic cells, but it also finds some use in non-aqueous voltaic systems like fuel cells and lithium-ion batteries, although these fields are out of this video's focus. The main use of ion exchange membranes in amateur chemistry is generating acids and bases from salt, such as preparing sulfuric, nitric, and perchloric acid from their corresponding readily available salts. On industry, the dominant use of these membranes is in the chlor-alkali industry, where sodium or potassium hydroxide and chlorine are produced from sodium or potassium chloride. Both of these applications have been demonstrated by YouTuber Scrap Science on his channel, and Nerd Rage also has a video producing sodium hydroxide from sodium bicarbonate, and I strongly recommend them. Other rather niche uses of ion exchange membranes are the purification of water via electrodialysis to remove ions, as well as enriching and separating useful metal ions from wastewater or mine solution. The details on these applications, such as apparatus design, cell reaction mechanism, and more, will be discussed in a future video. For the remainder of this video though, I'll focus on making the ion exchange membrane itself. But before we start to design our own ion exchange membrane, we can draw inspirations from the structure and synthesis of commercial membranes. Most of the commercial membranes, including the famous ones like Nafion and Fumacep, all adopt the shared structure of a carbon-based polymer backbone and charged functional groups attached along it. This structure is rather easy to synthesize, and there are 2 main ways to approach it. One way, polymer modification, is to start with the pre-existing unfunctionalized polymer and add the charged groups on a later modification step. Polystyrene sulfonate, the ionomer found in cation exchange resin beads for water softening, is prepared this way. Polystyrene is first synthesized from styrene and divinylbenzene, and then sulfonated with chlorosulfonic acid to add the negatively charged sulfonic acid groups. Similarly, the anion exchange membrane Sustanion also starts from styrene monomers, and undergoes an alkylation reaction with substituted imidazole to give positively charged pendant sites. The other way, copolymerization, prepares the charged polymer in a single copolymerization step. Nafion exemplifies this route by mixing tetrafluoroethylene and vinyl perfluoro ethers to generate a copolymer containing sulfonyl fluoride groups, which is then hydrolyzed into sulfonic acid. A combination of these 2 routes is also possible, which Fumacep FAA3 and Orion TM1 adopted, first constructing a copolymer chain and then transforming the halides to quaternary ammonium functional groups via a nucleophilic substitution. The other type of ion exchange membrane, known as ionines, is completely different in that the charged groups are located right on the polymer backbone instead of on side chains. This makes the polymer harder to synthesize but offers better performance, as the pendant sites are closely packed together. The representative ionomer, amion, is synthesized by a 2-step polymerization, first reacting diphenyl isophthalate with a biphenyltetramine to form a polymeric amide, which then undergoes an intermolecular dehydration to afford the benzimidazole ring system. The now uncharged heterocycle is further alkylated to give the final charged ionomer. As you can see, the synthesis of these polymers is really quite complicated. So I think that their high cost is perhaps justified, but still the expense is one of the key setbacks that prevent ion exchange membranes from being used in everywhere it should be. Besides the cost, the commercial membranes also has a common drawback on their weak mechanical strength due to their thinness of only dozens of micrometers. A scratch from a sharp electrode or a squeeze from a tweezer could break them, and after that the membrane is essentially defunct as solutions can just leak through it. Additionally, perfluorinated membranes like Nafion pose safety and environmental concerns during its synthesis and waste deposit, as toxic fluorine compounds are used to make it and may be released when the membrane is burned alongside other wastes. The polystyrene-based membrane materials share some common structural weaknesses, such as their brittle nature when moisture decreases and their poor resistance towards strongly oxidizing species like hydroxyl radicals produced during electrolysis. This is why ion-exchange resin spheres and sustaining ion membrane must be stored underwater at all times. Finally, many nitrogen-containing functional groups of anion exchange membranes like quaternary ammonium and imidazole may break down in concentrated alkali at high temperature through a series of pathways like nucleophilic substitution, Hofmann elimination, and even Sommelier-Hauser and Stevens rearrangements. Efforts on designing better functional groups to slow down or prevent these degradation processes is also very interesting. For example, adding sterically hindered groups on the unsubstituted imidazole ring, especially at the labile 2 position, can minimize or prevent hydroxide ions from attacking the ring and hydrolyzing it. Also, adopting quaternary ammonium with a cyclic structure can achieve far better stability than using longer carbon chains to bear the trimethylammonium group, because the cyclic structure resists ring opening elimination due to a strain transition state. Anyways, that's a bit of a digress, but at least now we know what the key drawbacks of commercial ion-exchange membranes are, and how engineers and scientists manage to work through these problems by designs and trials. Still, the problem of weak mechanical strength cannot be solved by simply altering the functional groups on the membrane. Instead, a new inert support layer such as PVC, PP, or even glass fiber can be added beneath the active ion-exchange polymer, the result of which, known as heterogeneous membranes, have much better mechanical strength than the previous homogeneous membranes, as the strong support layer prevents the ion-exchange polymer from easily breaking. The exchange is a higher electrical resistance as well as a lower ion permittivity and selectivity than the homogeneous membranes. The acid and base resistance of those membranes are also unknown and require further experiment testing. But the key advantage of heterogeneous membranes is that they can be prepared easily from household or commodity materials, instead of relying on exotic monomers and polymerization conditions. Now I'll introduce 3 types of amateur ion-exchange membranes, each adopting a different technical route and has varying cost, complexity, and properties. First up, the ion-exchange resin membrane, first developed by YouTuber Rowow based on an academic paper, and then promoted by Nycalc and Light. The idea is to use the easily available ion-exchange resin spheres as the ionomer component and fix it on a PVC-based membrane structure. As there is no need to make the ionomer from scratch, the procedure is incredibly simple. The commercial cation or anion exchange resin is first grinded in a lab pulverizer to a fine powder, paying extra attention on not to leave the resin dry and exposed to air. The powder is then mixed with PVC cement in a 1:1 volume ratio and painted onto glass fiber cloth substrate before drying out to give us the final membrane. For those who don't know, PVC cement is essentially PVC powder dissolved in an organic solvent like THF, so it can produce a uniform film of PVC when applied to the surface and allowed to dry. The process is very simple, but the membrane has the highest electrical resistance out of the 3. In more detail, the resistance depends very strongly on the fineness of the resin powder, which is why a lab pulverizer is recommended instead of a household grinder. Also, the ratio of powder to PVC cement must be high enough for the membrane to have a reasonable resistance, which in turn requires adequate mixing between the two to allow the resin powder to fully disperse within the cement. Finally, the membrane doesn't expand or contract when switched between different ion forms like between sodium and hydronium, which some commercial membranes like Nafion do, hence lowering the risk of breaking. As mentioned before, the structure of polystyrene sulfonate implies that the membrane may be attacked by acids and bases as well as strong oxidizers. The second type of membrane is ionic polymer membrane designed by MysteriousBhoice. He found a way to construct a working ionomer from citric acid and polyvinyl alcohol, which I was honestly quite surprised. First, a cleaning cloth is painted with PVC cement and allowed to dry, creating a basic PVC coating. The cloth is then soaked in sodium hydroxide solution with a little quaternary ammonium salt as phase transfer catalyst, which serves to partially dechlorinate the PVC and create hydroxyl groups on its chain. After rinsing with water to remove alkali, a mixture of 20 grams PVA glue and 5 grams citric acid is painted on the cloth, which is finally baked at 150 degrees C for 45 minutes and rinsed with water again to afford the final membrane. This type of membrane has a more homogeneous structure than the ion-exchange resin one, giving it better performance. I deduced that the ionomer layer is formed by the citric acid cross-linking PVA and dechlorinated PVC chains together, with its 3 carboxyl groups forming esters with the free hydroxyl groups. Not all of the 3 carboxyls will be condensed though, and the remaining free carboxyl groups act as weakly acidic ion transfer sites, forming a cation exchange membrane. Based on this polyester structure that tends to hydrolyze, I assume that the membrane is unstable against strong acid and bases, especially at high temperature. MysteriousBhoice also reported that using glutamic acid instead of citric acid can create anion exchange membranes, but the results from test trials are rather mixed, so I'm not going to present it as a working procedure here. Overall, I think this membrane hits a good balance between cost and performance out of the 3. The final membrane we're going to look at is from YouTuber Daniel Rosselli, and it has the highest degree of similarity with commercial membranes, especially on that it doesn't require an inert support. First, 10 grams of PPA is mixed with 5 grams of polyvinyl pyrrolidone or PVP and dissolved with water, poured onto a flat solid surface, and dried for a day. This step directly forms a stable polymeric membrane. Next, the membrane is cross-linked by soaking in a mixture of glutaraldehyde, hydrochloric acid, and acetone. Finally, the membrane is basified using a potassium hydroxide solution under heat and stored that way. This membrane uses more exotic and expensive materials out of the 3, but it probably has the lowest resistance and best performance due to the absence of inert support. My deduction for the cross-linking steps reaction mechanism is that glutaraldehyde condenses with the amine nitrogens on PVP to form charged imines under hydrochloric acid catalysis, and these imines are later stabilized by alkali to form ionic groups, although I'm still skeptical about this mechanism's practicality. The membrane is presumably more stable to acids, bases, and temperature due to its unreactive amide linkages, and has an overall property closest to commercial ion exchange membranes. Even the yellow-brown color matches as well. In conclusion, a basic overview of ion exchange membranes, a breakdown of the commercial membrane technology and drawbacks, and 3 unique methods for amateur ion exchange membranes are presented in this video. Again, I give full credit to the 3 YouTubers that made their great contributions to the amateur chemistry community with their innovations, and be sure to check out their videos if you want to replicate their designs. I hope you find this video interesting and informative. See you soon.